purpose of this video is to review the answers to the exam questions in the rates of reaction booklet. The first question is asking us to draw a second curve to represent the energy distribution on this Boltzmann curve for the same number of molecules at a high temperature. Now, if there are the same number of molecules present, we're trying to get the two graphs to have the same total area under the graph the same. Now, what happens to higher temperature is the average kinetic energy of the molecules is going to increase. But because the area has to remain the same, I'm looking for a curve with a peak which is lower and in that direction. It may not be the best drawn curve, but it's fulfilling the criteria that the examiners are looking for. It's kind of the same area, but the peak, the maximum, has been moved to the right and is lower. Now, how, using this diagram, can we explain how an increase in temperature causes the rate of reaction to increase? Well, the activation energy is the same for both reactions. All we've done is increase the temperature. And I can see by increasing the temperature, I have increased the number of particles with an energy greater than the activation energy. Only the particles with energy greater than the activation energy, that's to this side, are able to react. But on this curve, which I'm going to say is the higher temperature, T2 is greater than T1, I have this new H box. So I could actually use this. This is representing the increase in percentage of molecules with energy greater than the activation energy. Okay? So at a high temperature, a greater percentage of the molecules have energy greater than the activation energy, as shown in the diagram. What we've got in question 2 is the kind of rate graph which you will be familiar with from GCSE. We've put some magnesium carbonate in some dilute hydrochloric acid, and we've measured the volume at regular intervals. And we can see clearly, if I were to plot gradients of this line, the rate of reaction is slowing down, and eventually, at this point here, when the graph goes flat, the reaction stops. The reaction stops because one of the reactants has been used up. So using collision theory to explain the change in reaction, as the reaction proceeds, some of these reactants are being used up. So if we think about, for example, the hydrochloric acid, as the hydrochloric acid gets used up, the concentration of the hydrochloric acid goes down. That means there will be fewer hydrochloric acid particles, call them whatever you wish. The concentration of hydrochloric acid will be less. There will be fewer particles or ions, or call them whatever, per centimetre cubed, and so the frequency of successful collisions will decrease. There'll be fewer successful collisions per second. So the rate of reaction diminishes, and then at this point here, the reaction stops because one of the reactants has been used up. Now in part C, we've used a weak acid instead of the hydrochloric acid. We're going to assume that the concentration of both acids and all of the conditions are the same. So same temperature, same concentration of acid, it's just that it's a weak acid. Now from GCSE you should be able to remember that a strong acid is one which fully ionises or fully dissociates. At A level we tend to use the terminology dissociates rather than ionises. A weak acid is one which only partially dissociates. So that means the concentration of the hydrogen ions in a weak acid of the same concentration as a strong acid, the concentration of the hydrogen ions will be less. So the rate of reaction will be slower. But eventually it will get to the same point because the concentration of the two acids was the same. So the examiner for the 2 marks is going to be looking for a slower reaction but eventually ending in the same place. Question 3 is very, very similar to question 1. We've got a Boltzmann distribution curve, but this time we want to do the experiment at a lower temperature. We're going to label this T2. Now, if it's a lower temperature, the average kinetic energy of the particles will be less. So I'm going to be looking for a peak which is higher and to the left-hand side. That line needs to go again over here. It must not cross the x-axis. Often in an A-level exam you're going to be asked to label these axes. This is going to be number of molecules and this is going to be energy. You can say number of particles. That will often be in the alternative marking scheme. And that is T2. I'm not going to go through question 4 yet. I'll do that when we have done the topic on equilibria.